Okay. Yeah, thank you so much for having me. Today I'm gonna kind of give mostly a big overview talk about how would we be able to get to intelligent agents that understand language in 3D. So I'm interested in developing these helpful AI assistants. And in particular, what I'm interested in is having these assistants be able to understand language in the context of 3D representations and 3D scenes. And because of this, I've also done quite a bit of work with large-scale interactive environments. And so our goal is that we would like to have robots that can help us around the house. And so here is an example. So this is a kind of a robot that would go and move the stuffed animal from the chair to the sofa. This is actually a fairly constrained language description where we're just trying to move some object from one location to another. And with this, you need to do a lot of different skills. You need to be able to identify what objects you're looking at, try to match it against the language, and also have the robot actually be able to navigate and manipulate the objects. So how do we actually get here? How are we able to achieve these intelligent home robots? So I believe that in order to do so, it's very important for the community to develop frameworks and benchmarks, as well as have methods that really are modular and use abstraction so that we can address separate problems independently. And in addition, it's very important to have pre-trained models that we can use. Finally, I also fundamentally believe that we want to be able to use language for task specification. So in this talk, I'm going to focus a little bit on the first and last point, which is the development of frameworks and benchmarks, as well as how we would use language for task specification. So over the last 7 to 8 years, we've actually seen quite a bit of development in simulation frameworks and tasks. Back in 2016, we had a fairly simplistic environments, such as this Mujuko, which is just this half cheetah, which is just on a flat plane, or this DeepMind Lab example where we have an agent trying to go about maze. But since then, we've had these development of simulators with much more realistic static environments, as well as this move toward more interactive environments where in AI24, there's this interaction, but it's kind of this disembodied interaction where you would have, let's say, this, you would have the agent not necessarily just have a magic pointer. More recently, there has been a move toward more diverse tasks with rich simulation. We have Behavior 1K, which has like over 1,000 different tasks. And there's much richer simulation as well with deformable objects and fluids where the robot can actually interact with these more complex dynamics. In addition, we've also seen these the introduction of these home human robot interactions in simulation frameworks as Habitat 3.0. And so what we're seeing that there's this trend toward more and more diverse tasks. And in order to support the development of these agents, we do need to define many different kind of tasks. And there are many different kind of tasks, ranging from navigation to pick and place to more high-level tasks such as cooking and cleaning or assisting humans that can be defined and addressed. And in order to support all of this, we need to have simulation frameworks and the data sets and assets that accommodate these different tasks. And with this, then we can start to investigate different approaches, whether it's using reinforcement learning, or what kind of maps should we use, or what kind of low-level skills should we be training these agents. And this is something that I think is very exciting, and I think we've seen there's quite a bit of development in this area with an increasing diversity of tasks and richness of interaction, as well as scale of environments. So for me, I believe that it's important for the community to work at all these different areas, and different people can work on different things. I myself have worked a bit on simulation frameworks. I've helped to contribute to both Sapien and Habitat 2.0. So with Sapien, we introduced the PartNet mobility dataset, which composed of over 2,000 objects across 40 or so categories, and with over 14,000 movable parts. And this is very exciting because it was this step toward having this interactive objects that you can then articulate and then you can put into environments. And so this enabled then people to do these experiments with these rich objects where you could investigate, whether how a chair, you can push it against a table. I think in this particular case, we wanted to focus more on opening and closing drawers, but you can use the chair to do so. However, this particular data set was limited in the sense that the objects were kind of independent and they were not arranged in scenes. So one obvious direction is to put the object in scenes, but other directions to also explore different ways you can use and manipulate these objects, which is what this is work from Hao Su's lab from UCSD, where this building on the Sapien simulator, it's developed to tackle many different manipulation tasks beyond just opening and closing drawers. In Habitat 2.0, we did start to look at actually interactive scenes where the objects are each of them are articulatable, and this then allows for, together with procedural clutter generation, to do a variety of rearrangement tasks that involves maybe moving object from initial position to a target position. And this requires kind of training together different skills, navigating from one place to another, picking up something, and then placing it, say, into a drawer. It also requires being able to open and close the drawer. And so this requires several different tasks. And this is only possible because these simulation frameworks are designed. And it enables for a variety of approaches to be compared. And so there's this little graph here that shows, there's different approaches. You don't need to care too much about the different approaches, but the red is say, a monolithic reinforcement learning agent versus something that's more modular. And we can show that, this is a pretty challenging task because it requires many different interactions. But the main thing is that by building these frameworks, we can then start to investigate and compare these different approaches. But built on all of these simulation frameworks, what it really needs is these assets, these data sets. And these data sets, they can either be scanned environments, or they can be synthetic things that are composed of multiple objects. And if you were to take these multiple objects and each of them were articulated, then you can have a rich interactive scene. But how can we actually build real-world interactive environments? So this is an example of a recent, well, maybe not so recent, but a project that we did a couple of years ago called Multiscan, where we actually tried to collect real-world data of where we went and we took scans of different environments. And we would take the scans in multiple, with multiple states. And in addition to this, we actually, so this is manually done. We annotated the different objects and their moving parts, as well as their articulations. And because we took the scan of the scene at different times, when for instance, with the cabinet doors are either open or closed, we can now match them between what it looks like when it's open and closed. But in addition, we also annotated the articulation parameters. So this allows us to create this kind of articulated scan that can be opened and closed. But you can also see that there's still some issues with this real world articulated scans, in the sense that because we only observe the scene at two static snapshots, what happens is that some of the parts of the object is incomplete. And for instance, this trash can, actually it's a printer, sorry, it's the lid, when it opens and closes, you see that it's kind of transparent, or rather it doesn't have a full surface. So this is a remaining challenge where we need to be able to complete the interiors. Nevertheless, this effort resulted in roughly 100 or so environments with 230 scans, because we scan each environment multiple times, and it consists of a large number of objects with articulated parts. And with this, then, it is a step toward having these real-world articulated environments. So I talked about the importance of developing frameworks and benchmarks. Now I want to talk a bit about why we want to use language in order to specify our tasks. So I'm a firm believer in the power of language, as that language is very expressive. We can describe a very large range of scenes at different levels of specificity. For instance, we can either use language to just say what the goal is, pick up the banana, or you can actually give step-by-step instructions, go out of the bedroom, go into the kitchen, go to the counter, look, the banana is to the left of the cup, pick it up, So you can have these different levels of specificity. And this is also human-centric in that most common tasks can be specified using language. In addition, we are all very aware of these astounding developments in large language models, as well as large vision language models. And by leverage language, we can really make use of the common sense knowledge that's captured in those models, as well as handle open vocabulary concepts, and also give people a very flexible way to express what they want. So here's just a brief example. So this is an example from RoboCasa, which is a work from UK Zoo at UT of Austin. And here you can see that they demonstrate that that in order to do different tasks in the kitchen, you may want to have skills like open door, push buttons, and they can be put together to do more complex tasks such as steam vegetables or restock kitchen supplies. But the main thing I want you to note is that language, in the end, is what is used to describe all these common skills and tasks. And if we were to use language for task specification, I've also talked about how I think modularity and abstraction and using pre-trained models is important. But if that's the case, then we can also say, okay, what are some good subtasks that we can define as submodules that are helpful as building blocks for whatever problem we want to solve? And the vision community has been very good. They have these trained object detectors, and language community also has defined, good tasks. For instance, doing summarization. But for us, we also want to if we want to have a robot that can help us around the house, there are also specific tasks that are useful. For instance, opening and closing drawers. But in the way of understanding language, we have tasks such as, being able to say, okay, if I wanted a robot to bring me my coffee cup, I feel an important task would be what's called visual grounding, or locating where the coffee cup is. So for instance, in this example, the robot need to figure out, hey, that's where the coffee cup is. And if it was this whole thing was in 3D, then if they can identify, oh, the coffee cup is 2 meters in front of me, and what objects they are, then they can plan and use a navigation module to go to the coffee cup. So another part of my work is that I do these different tasks that bring together language and 3D. I will talk about this visual grounding in 3D, where what we want to do is, in this particular case, we have a point cloud of a scene. So in 3D, we can use many different representations. In this particular example, we use a point cloud, and then we have a sentence. This is a bed with blue sheet. It is to the left of a desk. And what we want to do is we want to just identify which object is it talking about. And this is to show that it's actually in 3D, so we zoom into it. And this is the basic problem setting. And this is some work that we did in this project called Scan Refer that defined this task. There was a data set that was created for working on this. But in the original formulation, it was the setting was very strict, in the sense that the Scan Refer setting assumed that there was exactly one object that matched the description in the scene, which is not really realistic. In reality, if some people were talking about different objects or using language, it could be this particular case, and they were very exact, and only a single object was described, or maybe they were a bit more ambiguous, the description. They say this is a black chair facing the door, and it could have been any 3 of them. And that could either be because they just didn't think to be too clear, or sometimes they could even make a mistake and say this is a white cabinet, it is next to a desk. But in this thing, there's no white cabinet, so there's 0 target. In this particular case, what you want to do is you want to be able to handle this flexible nature of language, that maybe nothing was being described, or maybe it's multiple. And so what we did here is we actually took the original data that was used for the Scan Refer project and just used the large language model plus a bit of human verification to generate additional data for training and evaluation in this setting, where we would just randomly pair descriptions from Scan Refer with scenes from ScanNet, and these, because we're randomly pairing, that's how we would get the case where the person may have made a mistake and it didn't refer to anything. Or, we would take the original Scan Refer data and maybe improve it a bit by doing a bit of ChatGPT rephrasing to get a bit of diversity. And then for the ambiguous case, what we would do is take the original description, make it shorter, and then that will allow us to have more ambiguous cases. And this is how we would create this particular data set. And we were able to generate this data set. And here you can just see some examples where we would take the original description and then potentially modify, either trim it to make it more ambiguous, or we can modify it to potentially be a bit more diverse. And to address this problem, what we did is we used a 2-stage pipeline, where we took the input scene, which is a point cloud, and we would run object detector to detect the objects, and then we would then take that and match it against a text description to figure out which object is being described. And again, in this particular visual, I show just one object, but you could have it be a binary classification for each object to see if it matched or not. And in our particular case, we used point group for the object detector, and we used clip features where we render the different views of the object as well as the point group features and try to match it against a text encoding. And with this, this is just some quick example that shows that it is possible to identify that, the toilet is white and mounted on the wall, and that it's both of this. This was just a brief example of a problem that you could do with vision and language, and hopefully you can imagine how it's useful for robotics, where you would identify the object and then the agent would be then navigate to it. But since then, there has been some trends in visual grounding for 3D. One is that more recently there has been the use of unified models for multiple tasks, as well as the use of LLMs and large vision language models as well to generate more larger and larger data sets. And this allows us to expand out and to handle more complex scenarios. However, there's still many elements that are missing, in the sense that in this problem setting, there isn't necessarily what I would call fine-grained grounding, where you would match potentially a specific mention of an object to the object in the scene. And also, when we talk about things, when you use language is very flexible. We don't always just talk about objects. Sometimes we talk about a whole area, the dining area. It's not necessarily a particular area. Or we can talk about the space in front of the refrigerator. So that's something that's not tackled. And we are also not tackling spatial reasoning or doing systematic evaluation yet. So these are all challenges. But I just want to say that right now, I do think it's very useful for a language for task specification. It's often used as a goal in different tasks for robotics or embodied AI, for instance, for navigation instructions. And we can also use these, beyond using language for task specification, we can also use these, once we have it for task specification, we can leverage these large language models as a source of knowledge, and they can help us bridge with the language specification. And it can help us do planning and break down different tasks, complex tasks, into subclasses and actions and so forth. I think I should probably wrap up. I want to say that most of the work that I did present was done by my group, as well as collaborators. And in summary, it's important to develop simulators, task and data, plus the benchmarking of approaches. And I think in order to get to where we want, for intelligent agents that can have perception, learn, and planning and control, we really want to use language for communicating and a source of knowledge.
All right. Thank you so much, Angel. Yeah, in the interest of time, I think we'll take one question. Any questions? No questions? Okay. Okay. Oh, we have a question.
Hello. I just have one question about what do you think about the dynamic environment that the action have to interact with it as well, and just having the control the offline kind of finding way. I mean, what do you think? I mean, what can be done, or what are your suggestions in your group? Are you working on them as well?
Are you able to hear them?
I couldn't hear it very clearly, so
Okay,
could you
I
repeat?
can repeat it. Yeah.
Okay.
So the question was about, do you think about dynamic environments where the scene is changing, right? As the agent needs to interact with the environment, and it's not just doable directly with like a point cloud offline because the environment's changing. Is your group working on something like that?
So I guess I believe that it's important for the agent to construct, I guess I tend to call it map, but a memory of the environment. And what's important is that, of course, if things are changing, then what we need is a dynamic map, so that can handle, like, ask the so for the parts where the agent doesn't observe, it can remember what was there before. But when it does see things change, then it would update its memory to say, oh, this has moved from here to there. And so I think that's actually very important. And it's actually pretty challenging because, we also have right now noise in our perception, the agent's perception. So how do you distinguish changes due to noise versus actual real change is tricky, I think.
All right. Thank you so much, Angel, again for being here, especially when it's late at night on a Sunday.
Yeah, thank you so much for having me. And